Okay, guys, second stream of the day. Let me share the stream link on Discord. We are live. Let me just also reply here to Ashif. I want to contribute in this mentioned task as this. I'm going to have an interesting machine translation bit before contributing into core. Take your time. Even helping around data is super appreciated. Okay. So, the conclusion from the run I just made before, during the break, is that for some reason, we don't get any speed up improvements with fused atom, which is weird, to say the least. Because looking at the numbers here, 31138, and then here for the 1100, 31938, literally 8 minutes, which is the same as for the fused atom. And here we're using the old atom. So let's understand what's going on and how can we trigger the usage of fused atom V2. How can we grab this class? Why are we returning V1 and instead of V2? Let's try to understand that. So here it's obvious that this is used as a fallback. Let's see whether in the latest bear sec are we still using version 1 fused atom. Let's find that one. Let's just go to optimization. Okay, and then so it seems we are just using V2 as a fallback if there is an import error here. The deprecated quote unquote in recent versions of Epiphany is a bit faster than the main interface, since we don't use the Apex optimizer. This can be installed by passing the deprecated fused atom option when building. Okay, let's see. I think we've done that. Yes, we did. So it's interesting that we are not using fused and we are getting the same speed. Why is that? Let's see whether anybody complained about Apex. How to use Apex. Undefined symbol. Import error. Is there any mention of a slowdown? Is there any mention of a slowdown? Speed. As soon as somebody mentions speed or slowdown, let's just open that up and analyze. Okay, really slow. Let's go to the second page of issues. Bug. Okay. There is no mention of slowdowns. Is my training routine normal? We don't have errors, we just have okay. I get much faster speedups with a similar setup. At least 160k words per second. This has more to do with FP16 than with what we are looking for. Okay. Max tokens to change the batch size. What's the max tokens we're using? Let's see the setting we have here. Max tokens set to 2048. Let's see what are the configurations here. If we go to examples, let's find NLLB. Let's find the modeling part, the training part, the configs, and here we are. Max tokens 4096. Whereas we've set 2000. Where is our setup? I think this is the one. So max tokens is 2048. And max tokens here, if it's even mentioned, it is 200 only. 8,192. This sounds almost like batch, like context size, not like max tokens in the batch. Why are we not as fast? How can we speed this up further? That's the ultimate question. It's not clear why we are not getting any speedups from fused atom. Not getting any speedups whatsoever. Okay. So, guys, let's try and debug this. Train our current long JSON. Hello dev. Let's see why I did set the use old atom here. So that's basically triggering it to use. Okay, let's just enter and see what's the size of the batch. And then compare that to what an NLLB model used. I think that might be a valuable thing to do. Max update frequency. What's this one doing? What's the update frequency? Okay, let's analyze a couple of these. Let's see what update frequency does. Let's see. Warm up, learning rate, stop, clip norm, dropout. All of that makes sense. Max tokens. Let's see what max tokens is exactly. Not clear. Seed, log format, log interval. Let's see what log interval does as well. Log interval, validate interval updates. We don't really care about this because we won't be doing validation for now. Keep interval updates. Let's see, why is this set to 1? Keep last epoch. Let's see, why is this set to 1? Next source positions 512. Okay. Anything else that's interesting? Decoder length token. Lengths. Save interval updates. Save interval. Architecture decoder. Number of heads. Attention dropout. Disable validation. Okay, let's analyze these 5 arguments and understand what exactly they do, just to get some more clarity on the training side while we're waiting for the Stopes to finish. So again, in the background, Stopes is running, and it's literally those 2 processes for which we know that their directions contain the most sentences. So if we open up configs, directions, we are currently running these 2. They have 35 million or more, 35 million sentences. So that's the slowest one. Okay, Dev asked a question. When you started ML, was there someone who guided you, supported, or? Yeah, just internet. For me, it was just mostly internet. I did, like, even back at Microsoft when I was working, it was fairly independent. I was just learning on the job on my own. Okay. Let me just open the window, get some fresh air in here. Let's go. Let's analyze these. Go to train. Let me put them on the side here. Okay. And let's understand them one by one. Update frequency first. Max tokens. Log interval. Keep interval updates. Keep last epochs. Just to see whether the slowdown is coming from somewhere elsewhere, i.e. we are not letting our fused atom shine, because that's not the bottleneck for these trainings. Maybe, I don't know, just the first hypothesis that pops into my mind. So update frequency, let's see what that one does. Let's search for it. Okay, the update frequency option can be used to accumulate gradients from multiple mini batches and delay updating, creating a larger effective batch size. Delayed updates can also improve training speed by reducing inter-GPU communication costs and by saving idle time caused by variance in workloads. Okay, we've seen the paper we read earlier today is literally scaling. This is it. They're referencing the paper we read just this morning. Okay, interesting. That was a very good use of our time. Okay, so update frequency is basically that one. Okay, now it makes sense. Let me just see, where are these readmes coming from? Getting started. Oh, okay. Let's read this. We actually never took the time to read a bit more about FairSec. It's gonna come in handy now that we are using it to train. Let me open up FairSec. Okay, let's find this particular file, docs, getting started. Let's just skim through this, trying to learn a bit more here. Okay, training, generation, advanced training options. I guess that's what we are interested in. Okay, FP16. I'm fairly sure we have FP16 enabled in our launch.json as well. Let's open up launch.json. FP16. Whoops. FP16 atom stats. Huh. Are we using FP16 for our model weights? Let's see. That's another question we have to ask. Are we actually using FP16? If not, then why not? Why is it? Let me just check one thing. When we ran, let's go to modeling transcript. Did this mention FP16 anywhere? Okay. Training config. Not set. But even if it was set, would we get memory efficient, atom stats? Okay. No mention of this whatsoever. Training config. That's the main config, but then when we start calling, we never pass. Huh, okay, we'll see what happens there. Are we using, that might explain why we need so much memory at the moment. Distribute the training. Okay. Okay, makes sense. Let's continue. Adaptive span. Understanding back translation scale. We read that, okay, we read that paper as well today. We read 2 of the papers that were just referenced over the last 5 minutes. Wow. I mean, they are one of the most cited papers in the MT literature, I guess. Okay, so we know what's update frequency, and we know that we have it set to 1 at the moment. That's fine. For now, that's good. Now let's see whether we are using FP16 or not. When we load the model, let's go to train. Is FP16 mentioned here anywhere? No, it's not. So when we are loading the model, building the model, if we run until here, can we just check the data type somewhere? Let's see what's going to be the data type here. Okay. Model. Can we do data type? I guess we cannot. If we do parameters, buffers and stuff, process group model, can we extract anything from it? Can we do wrap module, FPV module, encoder, layers of 0, okay, and then FC1, and then D type, okay, FC1, how can we get the weights? Let's see what's the option here. Can we do parameters? How can we just grab that information there? Let's see. Why are you so slow? Come on. Okay, just stop. Just stop. Just stop. Okay, let's just put a breakpoint there and kick off the training, because that's going to be faster than waiting for VS Code to open the file. Okay. Will we have FP16 here? Yes, we will, but it's coming from common. So let's go here. Let's grab the arguments. And let's see what we have for FP16. Okay, FP16 is set to true. That's cool. So now let's go all the way up there to where we load the model. Okay, just find the build model line and run until then F5. Hit F5 until we hit this line here. And then I quickly want to see what's the setting. Fix, find, gradient. Okay, no mention of FP16 there. No mention here. Let's just enter. Okay. And then the model set to FP16 here. Let's just enter quickly here. Build model. Okay, we went through this code multiple times. Enter the build model. Share all embeddings. Build the model. Okay, build the embeddings. Enter here. Stable. Number of embeddings, blah, blah, blah. Init model. We can just skip over all of this. And then hit F10. Okay, we built that one. Where do we convert it into FP16? Any mention of FP? Nope. Or half? Nope. Okay, let's just then exit from here. Let's remove this breakpoint. Exit, exit, exit. Build the model. Quantize the model. Where do we specify that it's going to be FP16? Why is it not clear? Okay, I'm gonna stop this again and rerun it. FP16 needs to be used somewhere. Okay, run. Where do we specify it? Base architecture. All embeddings. Let's go to here, enter. FP, F. Okay. Huh. So it is allocated by default as the FP16, or no? Init model on GPU, false. Why would we initialize model on the GPU? Or conversely, why not? Okay, so this is definitely FP32. FP32 D type for the weights. Let's continue. So this is FP32. So again, we pass in those here. Let's enter here. Enter, enter. Save the config. Dropout, layer, return. Embedding positions. Hit F5. Layers. And then we just keep on appending the layers. Where is the embed tokens used? Nowhere. We just save it here. And that's it. And we know it's currently set to, it's currently FP32 weights. Okay. Exit from here. And let's exit here. Let's exit here. Okay. Lazy index. Okay, exit. Next. Not clear what's going on. Do you guys still hear me? I see my OBS is struggling for some reason. Okay. And then build criterion. Completely not clear where do they actually cast to FP16. That's why I hate these big libraries. Do they do that in the train? Okay, we're gonna find everything we need. Let's enter here. Enter. Update frequency. If the update frequency is above 1, if epoch is number that then this. In that case, we grab this, otherwise this. Okay. And if it's bigger than 1, we use grouped iterator instead of the regular one. So that's for the gradient accumulation. Okay. And then for TPU, no, we don't care about the TPU. VNDB and stuff. Let's continue. Number of updates. Samples. Let's grab the samples. Are these samples? Okay, let's get some values from here. Net input. This guy is source tokens, and this is probably FP32 before we cast it. Okay, this is int. Sorry, this is int 64 because those are indices. And then let's enter the train step. Model train 0 grad. Let's see. Go through the samples, prepare the samples. Prepare the samples. If we're on CUDA, we move to CUDA, okay. On CPU, convert precision, false. We convert the sample by applying the half. Okay, apply the half to the sample, and then we end up with what? Sample samples. What do we actually cast to? What do we actually cast to? FP16. Let's see. Give me the keys of sample. ID, number of sentences, number of tokens, target. Input, tokens ID. So if we go and type in ID, and then let's try ID type. Okay. And then let's try after ID, we need to check net inputs. There is a source length, there is a previous tensor. What does it even mean then to apply a half? Let's continue. Hello, Sergey. It's going good. We've done a ton of work in the previous stream. I'm now just going through some parameters and trying to figure out what's going on. I'm not sure where the conversion of the model to FP16 happens. I installed Apex last night, and I tried to profile, and it seems that with fused Atom, we get the same performance as without it, which is weird because I expected that Apex is gonna speed up things, and that if we use a fused optimizer, that's obviously should have sped up things, but that did not happen. So I'm now trying to just understand what's going on. Let's enter it here. Train. Set the number of updates. What does this even mean? Set the number of updates. What does this mean? Apply. Module up. What module is this? Dropout. Apply this. Anyway, I went too deep into the rabbit hole. Let me see what's going on. Let's go to the progress, train step, enter here, model train, enumerate, go through the samples, prepare the sample. Let's again enter into the train step here. Set it to train. Okay, I'm gonna skip this part. Let's go. Forward pass. Let's see what's going on here. So sample, number of inputs. This is obviously gonna be the type of this should be, oops, in 64. But once we enter and convert this using embeddings, that should be cast to FP16. This will also transfer FP32 parameters to self-compute type. Float 16, okay. Compute D type is set to float 16. Rebuild the full parameters. All gather full parameters. Why would we do that? This will also transfer FP32 to FP16. Okay, this is some fair scale stuff now. We're getting deep into the model inner workings. If mixed precision or move, if self move to CPU, we need to cast the FP32 CPU params to CUDA for the old gather. Yeah, no worries, Sergey. We covered two very exciting papers in the previous stream. That might be interesting. This is a bit more hardcore. I'm just trying to figure out some stuff. What's P data? Let's see what's the current device. It's already on the CPU, man, on the CUDA. Okay, the size. Okay, this was super hardcore. if CPU when we are exiting, otherwise clear, return false. Okay, well, that sucked. We didn't learn anything. We literally learned nothing. Let's wait for the next step. And there is a process failed because we were trying to be smart. Okay, let's rerun the train. Remove all of this. Okay, let's hit the train step. Hit run. Okay, let's put a breakpoint there. Okay, let's put a breakpoint there as well. Let's enter here. Okay, we are in the forward pass. Let's go here. Enter. I think I clicked F11. Sometimes this code is slow to react. And if I click once more, then we might overstep. Let's see. Come on, come on. Why are you glitchy? Okay, maybe we have to run this one. Okay, now we can do F11. Let's just put a breakpoint here. Fair scale. I wonder how active fair scale is. Okay, it doesn't seem to be too active. Okay, something is stuck here. Let's see where the other one is. Okay, okay, okay. Here we are. Okay. Let's go. Enter the forward. Enter here. Forward pass. Okay. Encoder. Source tokens. Source length. And return null hidden. Let's enter the encoder. Okay. And here we are. forward the embeddings. Let's see, embed the tokens. Okay, so let's see what's up with the weight. What's the D type? FP16. When did that happen? Why is this so not transparent? I mean, that's a good result, but I really want to know exactly when that happens. D type, FP16. And now we grab that and we get X, which is also going to be FP16. And then we just do some addition and we get X, which is going to be FP16, of course. And then drop out. And we end up with X being FP16, encoder embeddings being FP16, transpose, create some dictionary. Let's see where we go through the layers. Here we are. We go through the layers. We grab the, okay, here's the past source tokens. X, again, X, D type, FP16. Let's go through the layer. Let's call it. Okay. Attention norm. Let's enter there. Fuse layer norm. Let's enter here. Let's see where we can enter here actually. Apply. Okay, we are in the fuse layer norm of the apex. How come we are in apex when... Can we disable apex just for the sake of testing without and with? Currently using old Atom, but okay. Okay, here's the weight. Let's see the shape, and let's see the D type, FP16, and input and bias. So everything is FP16. That's good. So self-attention, let's enter there as well. Let's go inside here. Bias. Here are some weights, and again, this is FP16. Okay, so everything is running in FP16, but the thing that's not clear is when do we get, when does that get, when does that happen? When do we convert the weights into FP16? Because during construction, that's not happening. Okay, for now, I can leave this as it is. I'm happy that I know that we're running on FP16. I'm gonna stop this. I'm gonna stop the whole training run. Can we disable Apex? Or is it just being used by default once we install it? And there is no way to go back? Nah, nothing popping up there. Okay, let's see what's max tokens. What does max token does? Max token 4000, what does that do? The batch size is specified in terms of the maximum number of tokens per batch. You may need to use a smaller value depending on the available GPU memory on your system. That's how I understand it, but then it doesn't make any sense. Why would you... What's the batch size in the paper? What's the batch size in the paper? Let's see that. Batch size. This is what? Mining, monolingual data, related work, student teacher mining. Batch size there is 10K, but okay, these are laser models. All models are trained with an effective batch size of 1 million tokens per update. Okay. This is what we're looking for. So they say 1 million. Did I note that down somewhere? We go up here. If we go to, let's see. I think I mentioned that somewhere. Okay, I'll have to find where. I wrote it down somewhere, but I can't remember where. I don't see the... Huh. Okay. So they mentioned 1 million. Okay. Again, paper. We train a dense transformer encoder decoder with 1.3 billion with the model dimension 1024, blah, 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 blah. All are trained with an effective batch size of 1 million. We optimize with Atom. We linearly increase to 8,000. Okay. Let's go further. Could you know how old I am? Can you guess? We train the model for 300,000 steps using 4-phase curriculum. Very close. Very, 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 very close. We train the model for 300,000 steps using 4-phase curriculum. I'm 29. 1 million steps. The maximum sequence length is 512 for both the encoder and the decoder. Memory efficient FP16 for training. Okay. With label smoothing. Okay, so training details are on page 102 if I don't find stuff. 102 page if I don't find it. Okay, so that means 1 million. We should why are all the configs set to such a number that we can confuse it with context length? Let's see exactly how this parameter is used in the actual training without reading the README, because there are some confusing details here. Let's go. Why would anyone set so little tokens? Now this is better. Max tokens. Let's go, let's find this. Max tokens. Max tokens per batch. Tokens per sample. Okay. Okay, this is better. Now we're talking 4 million. That now is more indicative that they are using it the way they're describing it. Okay. Max tokens. Okay, let's just go with, instead of dash, underscore. Let's see how this one is used. Where is this specified? Save encoder. Infer, generate speech sample. Is there any mention in the train? Okay, train. Either with max tokens or batch size. Validate. How the heck is this used? Why is it so difficult in this library to figure stuff out? Do they have any documentation or something like that? Does Fairsec have documentation? Can I just go to documentation and say Fairsec documentation? Do I always have to go through the actual code base? Where is this described? Just find me this. this is not going to be any better than going through code. Here is just an assert. Where is config datasets used? Logging. I don't care about that. Train. Okay. Get train. We're in train in the main file, in the main function. Epoch iterator, train. Okay. Let's get to the train step. Where do we load the data? Where do we load the main one? Where do we load the training dataset? So disable validation. Where is the task load dataset? Except for here for validation. Okay, that's what I'm looking for. I remember it was used somewhere when we start iterating here. We call the train task epoch iterator. Does this one create? It might well be that here is where it happens. Okay, files to include Py files, only Py files, max tokens. Okay, this will be easier. Max tokens. Okay, get batch iterator max tokens. Laser distillation train script. Infer generate speech sample options trainer. Get train iterator. Okay, this is where we do stuff. Okay, I think that's it. That's the one we were looking for. Trainer. And then batch by size. So trainer. And let's put a breakpoint here as well. Batch by size. Fair-sig dataset. Adjust batch size. Okay. Okay. Let's kick off the run again. Let's hit some of those max tokens and see how that is used. And let me see how the stopes is progressing. In the background, is stopes ready? Or is it still running? It seems like it's still running. Let me just quickly check where do we stand. Filter line. Let's put a breakpoint there and let's see what is the number of, okay, 27 million. 8 more million to go. Let's go. Okay, so here we are. Load checkpoint. Hit F5. Hit F5. Okay. Get train iterator, load checkpoint. Okay, so here's the max tokens. Let's enter inside of there. Let's just enter quickly. Okay, max tokens is set here as well. Create batch max token. Let's continue. Enter inside here. Max tokens. Where are you used? You're used here. Okay, then let's exit. And then let's hit F5 here. Let's go. Okay. Here it is. Max tokens. Create the batch sampler. Max tokens, batch by size. Batch by size. Here's the number of tokens. And you're used here. Batch by size vector. Okay, hit F5, hit F5, hit F5, hit F5. We've been here. Let's wait until we let's see whether we It's so hard to find details that you care about when you're dealing with these libraries. So for example, let me see examples. 128 sentences. Okay, 920 tokens. So if I grab the net input, okay, so what's samples? It's a list. How long is that list? Okay. Grab me the 0th element. Grab me the net input. And grab me the source tokens. Okay. What's the shape? Okay. What's 128 times 16? Okay, so that means this sucks. This is actually used as they said it's used. But we need to increase that number heavily. Let's go to train script. Let's find the train script. So I'm looking for the train script. Max tokens is just past there. Okay, let's just set a much bigger value. If we go there, long JSON, max tokens, this needs to be like much bigger. They set a million, so because they've gone million, we can maybe go and do something like I don't know, like at least 50,000. And let's now see whether we crash the GPU. So let's go here, train step, samples. Where are the samples? We get the samples here. So let's just disable everything other than this, and let's rerun. And let's see what's the NVIDIA SMI, what's the occupation. So what's the occupancy of my GPUs? So currently a ton of space. Okay, let's delete model checkpoints. Just delete the save directory and rerun. Unless it's due to the 50,000 setting, which I doubt. We didn't even start loading the data yet. Let's go. $50,000 tokens. Here we are. Let's see. Okay. Samples. Net inputs. Okay, samples. Net input. Source tokens. Okay, that looks better. So it's preferring shorter lengths. And what's the number of tokens? 40,948. Okay. How do they pick that number? I don't know for now. But we at least know that this is being used the way we thought it's being used. If that makes sense. Okay. What's my consumption here? Okay, let's just hit F5, run this. Why are you failing? List index out of range. I have no idea why that is happening. Let's just not put any breakpoints. Let's delete again the model checkpoints. Let's make sure this is completely empty. It is. Disable all of the breakpoints and just hit the run. Sometimes the failure happens because there are two parallel processes running on both GPUs, and sometimes because I just advanced a single one, there is some crash that happens. Okay. Let's go, please don't crash. Failed. Why? Why are you failing? OOM. Huh. Yes, okay. It seems it is indeed the case that we are failing because of this. Let's reduce it to 10K. And let's rerun. Let's go to train, hit run, 10K. So they run 100,000 steps, but with way more tokens than we. Like 100 more tokens currently. Which means we have to run for much more steps to get to the same number of tokens. Okay, again, it fails. Okay, let's go and reduce it to 5,000. Why is it taking so much memory? With 600 million, how many, what would be expected? Like, I think Eleutheri had some, Eleutheri number of parameter, Neo-X. I think it's working now, but it's slowing down my computer. Attempting to recover. It's attempting to recover from again OOM. So we can't literally cross. Oh my god. Everything is stuck because I'm pushing the system to the edge. This simply does not work. I was very optimistic to run with 50,000. Okay, just stop, bro. Just stop. Okay. I think these guys had some Rule of thumb. Four bytes, 2 bytes. Training. 4 bytes per parameter. Optimize your states. Okay, this is a very good, very good blog for some basic computation. Basic requirements for transformers. We can check out this blog maybe later. Yeah, I'm gonna add this one to read it later. Read this blog. I have added it as a to-do. Okay, going back to long JSON. So let's try 3000. Like 3000 should work because we were running with 2048. If this doesn't work, then that's weird. Okay, looks like this is working. Although it's super, my computer is getting very laggy. So let's see what's the consumption. 1821 on this one. So almost 24. So we can probably push it a bit higher. I'm just curious to see what's the top we can get to. Let's just put this to 3.5K. Let's rerun. Okay, but in bottom line, we now know what max tokens does. I'm not sure how exactly, what's the logic for figuring out the exact batch shape, the batch shape. How do they pick the number of sentences versus the actual length of those sentences? Okay, this is working. Actually, it's not. If we take a look. Okay, nothing is working again. The computer just gets stuck. I can't even open up my terminal when I start hitting these OOMs. So yeah, we cannot go above 3000 on my system with the current memory, with the current number of parameters, which is 615 million. Okay, let's just stop this. The whole system is frozen. I don't know, guys, if you can still hear me. I'm still here. I'm still alive. It's just that my GPUs are dead. Come on. Come on, unblock. I can't use my GUI. Everything is stuck except for my mouse. Okay. Almost there. Okay, just a second. Why didn't my VS Code crash this? Just crash it. Oh my god. Guys, did you hear me over the last 2-3 minutes? Because my system was completely frozen due to the excessive usage of my GPU. At least we know that with 3500 we are completely dead. So 248 it is on this system for now. We'll see how this works. Okay. Let's see what's log interval. There's a couple more parameters I want to understand. Train log interval. What does log interval log? Log updates interval. Let's see. Train script. Infer trainer. Okay. Let's understand what this does. Log progress every n batches when progress bar is disabled. Okay, let's see how this is used. Aha, okay. Yeah, okay, that's literally the reason we are seeing every 100 steps, we are seeing the log intervals. Okay, fair enough. Let's see how it's used. Here, and then here, log the stats. Makes sense. And what's the keep interval updates argument? Let's just understand what this one is used for. When used with this, skips deleting any checkpoints with update X, where X is modulo keep interval updates pattern. Not clear what this does. Let's see here. Something to do with checkpoints, but not completely clear. Okay, keep the last n checkpoint saved. Aha. With saved with save interval updates. Okay. So this just helps us keep the last. It keeps a single checkpoint. And we do that every 1,000 steps. Okay. Keep last epoch. What does this one do? No idea. If this is bigger than 0, keep last epochs. We set that one to keep last epochs to just 1, which means if it's bigger than 1, we grab the checkpoints and all of them, we remove them. Okay, again, this is just for all reasonable settings for keeping the checkpoints. Okay, just getting some feeling for the arguments here. So now getting back to the question that started this whole journey, and that's why do we have the same type of speed with and without this argument here, use old atom or FP atom stats. So whether we use fused atom or not, we get the same speed up. I think it has to do with the fact that now we just use Apex everywhere after we've installed it, and we can't really undo that. We can delete this. And now let me just find the fused atom V1. This one should be used. Let's just confirm that. Run the train. We should hit the init of the fused atom. True. And then we use the fused atom. But the thing is, no matter whether we are using this or this one, we get the same speed up. That's completely weird. Okay. Running this in the background. just to see whether we still get the same 8-minute speed as if we were not running with Fuse one. Let me see whether they mention curriculum anywhere in this code base. Okay. Can go bigger than 3,000 tokens. Just writing some notes on my side. Otherwise, I'm getting OMs. Let's see if there is any mention of curriculum. Curriculum. Don't shuffle batches for first and epochs. What does shuffling has to do with curriculum? Shuffle only if you're bigger than the curriculum, then you start shuffling. Interesting. Let's remove this requirement and let's see where curriculum is mentioned. Okay, in a ton of files, most of them are just these parallel corpus files. Is curriculum learning supported? How can we modify the data set such that we start including lower resource languages later down the training? Let's see. Okay, curriculum is not mentioned anywhere. Files to exclude if they have Latin. Okay, that was a very good way to exclude it. So no language left behind. Here's a couple of mentions of curriculum. Curriculum. Use the following parameters for training with either naive or phased curriculum approaches. Okay. So restore file, max updates. This is not clear. Not clear at all. Set this so that there is a consistent saved directory across all phases of the curriculum. Resume finished. Max update string. Restore file. What's restore file? What's this setting? So we have restore file. We have max updates. We have max update string. And we have resume finished. I just need this. Okay. Let's see. What does restore file do? Exclude, maybe exclude YAML files. And now let's see what restore file does. Path to pre-trained. Except you may need to specify the restore file in fairsec checkpoint and reset optimizers. We typically do fine-tuning on 2 GPUs. So what does this do exactly? Restore file. Restore file. File name from which to load checkpoint. Okay. Isn't this automatically figured out already? Aha. Continues from this checkpoint unless the checkpoint indicated in restore file option is present. Test string, test binary. Let's see a restore file with dash instead of underscore. What do we get there? Restore file, restore file. Test, test, test. Okay. Where is it called exactly during the... I'm expecting to see that in the checkpoint utils. Okay, I do see it here. So if the config is set to checkpoint last, then do okay, this is just a logic to decide. Let me stop the run. My video should be less glitchy now. As soon as this stops, please stop. Okay. Let me see how many minutes. 43:36. And we started at 35:30. So roughly 8 minutes. Okay. And it seems it's the same speed without the fused optimizer, which is weird. And I'm sure that it's actually loading the fused one versus the regular one, yet the speeds are the same. That's super weird. Okay, so this is used to just figure out the checkpoint path. If suffix is not none. else checkpoint is this? Okay. Max updates, I think that was the one we've seen already in the train script. No, this was the update frequency. What's the max updates flag? The max updates flag. Is that the one that stops basically the training once we hit over it? Max updates. Max updates. Let's see what this flag does. There is no mention of this flag. Interesting. Max updates. Okay. Only here. Tree stage. Phase ratio. Tree stage. Learning rate schedule config. Is this even used? Like, there is literally no mention of this variable in the code. It's just mentioned in the readmes and nowhere else. Literally nowhere else. What's the max update string? Maybe we can find it using this one. Save directory key. Given the value, we return this or this. Train script. Okay. Let's try with dashes instead of underscores. And see whether that one is mentioned anywhere in any meaningful context. Okay, these two are completely not used. It's probably just some bug because this is old NLLB branch. They're referring to that in the NLLB README, but I don't see any mention of those. I'm gonna put those as a note in my Notion. Curriculum. These two vars are mentioned in the NLLB README, but I don't see them actually used anywhere. Okay, let's maybe see whether somebody complained about this before. Here's the issues. Max updates, 7 closed ones. Oh, wait. So what they're saying here is, okay, here's the checkpoint. So we basically, okay, got it. They basically train with initial data they stop the training. They modify the, do they manually do this though? They modify the data such that we now include lower resource languages, and then they kick off the training with certain max updates for that particular stage. And then okay, but like it's still not clear. These two variables are not actually used. Let's resume finished. Let's see what this one is about. Resume finished. This is some Slurm stuff. Aha, resume finished. Okay, so resume the finished run is resume it from here, from the checkpoint specified with that path, and for that number of max updates. Okay, let's see where this is called other than here. Train script, resume finish. Let's see whether we can find anything with the dash instead of the underscore. Force any runs that finish to begin again, uncommon. So how do you specify dry run? So where does that happen? Okay, let me just stop this and reopen it up because linter died. Open up Versec. Okay, you can now see the colors, and now when I click F12, it actually goes immediately to the definition. Is job valid? Dry run. Launch train. Dry run. Just returns the argument. Okay. Let me see whether there is any mention of curriculum in Versec. Versec. Oops, not curriculum. Let's see whether these two words are mentioned in the same issue. Okay, just that one actually. So here's 13 bytes of memory per parameter for GPT-NeoX. So that means with 1 billion, roughly 13 gigabytes. Versec seems to be more memory intensive. Curriculum. Let's quickly skim through this. Curriculum learning. Add it back. Huh. It's not clear how does one run curriculum learning other than running manually, which we can do, which is painful, or we can implement it ourselves. But for now, it's not really clear how does one do that. Okay. Not really insightful going through this. Is there anything here? Nobody replied. Let's read this blog. That's one thing I want to do. And then we can go and play with mine data a bit. And finally, I need to find where did I lose that information. Laser to-dos. Let me search on my Notion. Stage. I must have accidentally deleted it. I'll have to double check on some of the streams. Check this out offline in one of my streams. Updates. Okay, guys, let's read this blog. I'll need this information to later understand a bit better this whole topic and figure out how much compute and memory we'll need for bigger models. It's 6 p.m. In 30 minutes, I'm wrapping up this stream, so that means we have the time to read this slowly and maybe a bit more time to play with mine data. Let's make a small break here just to, before switching the context to this, I need a bit of a break for my brain, and then we can continue, if that makes sense. So quick break, 3 minutes, stretching the legs. Be right back. Okay guys, catch you in 3 minutes. Okay guys, we are back. Let's go. Let's read this blog. We present basic math related to computation and memory usage for transformers. Okay, a lot of basic important information about transformer language models can be computed quite simply. Unfortunately, the equations for this are not widely known in the NLLB community. The purpose of this document is to collect these equations along with related knowledge about where they come from and why they matter. Note this post is primarily concerned with training costs, which are dominated by VRAM considerations. For an analogous discussion of inference costs with a focus on latency, check out this excellent blog post by Kipley. Nice. Okay. Compute requirements. The basic equation giving the cost to train a transformer model is given by roughly 6PD, where C is the compute required to train the model in total flops, floating point operations. The forward and the backward. Forward is roughly 2PD, backward is roughly 4PD. Okay. Tau is the aggregate throughput of your hardware setup, number of GPUs times the actual flops per GPU. Okay. T is the time spent training the model in seconds. P is the number of parameters in the model. D is the dataset size in tokens. Interesting equation, okay. So again, obviously the bigger the either the dataset in tokens or the number of parameters, we have to spend more compute training such a system. These equations are proposed and experimentally validated in OpenAI's scaling laws paper and DeepMind's scaling laws paper. Please see each paper for more information. I did read both of those before, but I forgot about these formulas just because I never had to actually compute it. It's worth taking an aside and discussing the units of C. C is a measure of total compute, but can be measured by many units such as flop seconds, which is in units of floating point operations per second times the amount of seconds, GPU hours, which is the units of number of GPUs times the number of hours you use to train on those GPUs. Scaling laws tend to report values in petaflop days, okay, which is the 10 to the 10 to the power of 15 times 24 times 3,600 total point operations. Okay, so that means running 1 day with petaflop per second compute. So this is 1 day in seconds times this amount of compute per second. Okay. Or GPU hours, which you care about more if you're paying to rent on demand or whatnot. One useful distinction to keep in mind is the concept of actual flops. While GPU accelerator white papers usually advertise their theoretical flops, these are never met in practice, especially in distributed setting. Some common reported values of actual flops in a distributed training setting are reported below in the computing cost section. Note that we use the throughput time version of the cost equation as used in this wonderful blog post on LLM training costs. Okay. Parameter versus data trade-offs. Although strictly speaking, you can train a transformer for as many tokens as you like, the number of tokens trained can highly impact both the computing costs and the final model performance, making striking the right balance important. Let's start with the elephant in the room. Compute optimal quote-unquote language models, often referred to as chinchilla scaling laws, after a model series in the paper that gave rise to current beliefs about the number of parameters. A compute optimal language model has a number of parameters and a dataset size that satisfies the approximation. Number of tokens equals 20 times number of parameters. So let's just read it again. Often referred to as chinchilla scaling laws, after the model series, blah, blah, that gave rise to current beliefs about the number of parameters. Compute has, okay, this is optimum in one very specific sense. In a resource regime, we're using 1,000 GPUs for 1 hour, and 1 GPU for 1,000 hours costs you the same amount. Okay, so for a given compute budget, if your goal is to maximize performance while minimizing the cost in GPU hours to train a model, you should use the above equation. That's why it's called compute optimal. We do not recommend training LLM for less than 200 billion tokens. Although this is chinchilla optimal for many models, the resulting models are typically quite poor. For almost all applications, we recommend determining what inference cost is acceptable for your use case and training the largest model you can to stay under that inference cost for as many tokens as you can. So let's read it again. We do not recommend training an LLM for less than 200 billion tokens. I mean, that's a weird statement. How do you define LLM? Like, if you have a 1 billion parameter model, do you want to train it for 200 billion tokens? Although this is chinchilla optimal for many models, and what does that even mean? Because by this equation that precisely determines the actual model size. The resulting models are typically quite poor. For almost all applications, we recommend determining what inference cost is acceptable and then training the largest model that has that inference cost, and then spending as many tokens as possible, which means that depends on your compute. Okay, engineering takeaways for compute costs. Computing costs for transformers are typically listed in GPU hours or flop seconds. GPT-NeoX achieves 150 teraflops per second per A100. So that's the throughput per GPU with normal attention, and 180 teraflops per second per A100 with flash attention. This is in line with other highly optimized libraries at scale. For example, Megatron Deep Speed reports between 137 and 163 teraflops per second per A100. As a general rule of thumb, you should always be able to achieve approximately 120 teraflops per second per teraflop per second per A100. If you're seeing below 115, there is probably something wrong with your model or hardware configuration. With high quality interconnects such as InfiniBand, you can achieve linear or sublinear scaling across the data parallel dimension, i.e. increasing the data parallel degree should increase the overall throughput nearly linearly. Shown below is a plot from testing the GPT-NeoX on Oak Ridge National Lab Summit supercomputer. Note that V100s are on the x-axis, while most of the numerical examples in the post are for A100s. Okay, it's a bit sublinear here, as you can see. Memory requirements. Transformers are typically described in terms of their size in parameters. Just a second, let me see one equation there. However, when determining what model can fit on a given set of computing resources, you need to know how much space in bytes the model will take up. This can tell you how large a model will fit on your local GPU for inference, or how large a model you can train across your cluster with a certain amount of total accelerator memory. Model weights. And here is just how many bytes depending on the data type, and then the structure of the actual data type. Most transformers are trained in mixed precision, either FP16 plus FP32 or bfloat 16 plus FP32. This is the compute data type. This is the storing of the weights. This cuts down on the amount of memory required to train the models, and also the amount of memory required to run inference. We can cast language models from FP32 to FP16 or even int8 without suffering a substantial performance hit. I think that's one of those unintuitive moments. So you can cast a model to int8, which is like literally what, 256 values, and still not lose a lot of performance. That's like Tim Detmer's work on quantization is just amazing. These numbers refer to the size in bits a single parameter requires. Since there are 8 bits in a byte, we divide this number by 8 to see how many bytes each parameter requires. So in int8, the memory of the model is 1 byte per parameter. Okay, this is 2 bytes and 4 bytes. There is also a small amount of additional overhead, which is typically relevant to determining the largest model that will fit on your GPU. In our experience, this overhead is less than 20%. Total inference memory. In addition to the memory needed to store the model weights, there is also a small amount of additional overhead during the actual forward pass. In our experience, this overhead is less than 20% and is typically irrelevant to determining the largest model that can fit in your GPU. In total, a good heuristic answer for will this model fit for inference is 1.2 times the model memory. Okay, so that's the compensate for the weights and for the actual activations during the forward pass. And then the memory is this, depending on how you're storing your model. We will not investigate the sources of this overhead in this blog and leave it to other posts or locations for now, instead focusing on memory for model training in the rest of this post. If you're interested in learning more about calculations required for inference, check out this fantastic blog covering blah blah blah. Okay, we've seen that one before. Training. In addition to the model parameters, training requires the storage of optimizer states and gradients in device memory. Okay, so for example, for Atom, you have to store what? You have to store the gradients, and the square of the gradients, so the exponential average. So that means you need at least 2, 3, because you have to store the model weights as well. So like, yeah, let's see. This is why asking how much memory do you need to fit model X immediately leads to the answer, this depends on training or inference. Training always requires more memory than inference, often much more. Okay, model parameters. First off, models can be trained in pure FP32 or FP16. In addition to the common model weight data types discussed in inference, training introduces mixed precision training such as AMP. This technique seeks to maximize the throughput of GPU tensor cores while maintaining convergence. The modern DL training landscape frequently uses mixed precision training because FP32 is stable but has a high memory overhead and doesn't exploit NVIDIA GPU tensor cores, and 2, FP16 is stable but difficult to converge. For more information on mixed precision, we recommend reading this notebook by Tunibai. Interesting. Those are the same guys behind the Polyglot project. And this is in Korean. Note that mixed precision requires an FP16 or BF16 and FP32 version of the model to be stored in memory. Requiring mixed precision memory per model is 2 bytes per parameter times the number of parameters. This is not clear what they mean by this. Let's see. What do you actually mean by this? Plus an additional 4 bytes per parameter. copy of the model that we count within our optimizer state. So the optimizer, in the case, if we were to store the model weights, the exponential average of the gradients and the squares, that's already 12 bytes. And then we also have here for the mixed precision 2 bytes per parameter. So that's okay. Let's see. This was not that clear. Note that mixed precision requires an FP30 version of the model to be stored in memory. Okay, let's continue. Atom is magic, but it's highly memory inefficient. In addition to requiring you to have a copy of the model parameters and the gradient parameters, you also need to keep an additional 3 copies of the gradient parameters. Therefore, for vanilla AtomW memory optimizer, you need 12 bytes per parameter. So that's the momentum, as I said, variance, and FP32 copy. For 8-bit optimizers like bits and bytes, you need 6 bytes per parameter, because you need what? You need the copy of the parameters, 4 bytes, and 1 for momentum and 1 for variance. For SGD like optimizer with momentum, you need 8 bytes, because you need 4 for the copy and 4 for the momentum. Okay, this is roughly the number I had in my brain as well. Gradients. Gradients can be stored in FP32 or FP16. We see that it therefore is stored in FP16 or FP16 mixed precision training. So their contribution to memory overhead is given by 4 bytes per parameter, or in FP16 case 2 bytes. Okay. Activations and batch size. Modern GPUs are typically bottlenecked by memory, not flops, for LLM training. Therefore, activation recomputation / checkpointing is an extremely popular method for trading reduced memory costs or extra compute costs. Activation recomputation checkpointing works by recomputing activations of certain layers instead of storing them in GPU memory. The reduction in memory depends on how selective we are when deciding which layers to clear. But Megatron's selective recomputation scheme is depicted in the figure below. Okay, let's see this. Parameter and optimizer state memory, activation memory, baseline, present work, baseline, present work, baseline, present work, baseline, present work. Okay. Where the dashed red line indicates the memory capacity of an A180 gigabyte GPU. And present work indicates the memory requirements after applying selective activation recomputation. See reducing activation recomputation in large models. Okay, I did read this paper, I think. For further details and the derivation of the equation is below. The basic equation given the memory, giving the memory required to store the activations for a transform model is given by this. If there's no recomputation activations, selective recomputation, full recomputation. Okay. Where S is the sequence length in tokens, P is the batch size per GPU, H is the dimension of hidden size within each transformer layer, L is the number of layers, A is the number of attention heads, T is the degree of tensor parallelism being used, 1 if not. We assume no sequence parallelism is being used. We assume the activations are stored in FP16. The traditional recomputation necessary also depends on the selectivity of the method, but is bounded above by a full additional forward pass. Hence, the updated cost of the forward pass is given by between 2 PD and 4 PD. Okay, this one was, they lost me here for a second. Let's see what's going on. Okay, so they compute in, this is the memory required to store the activation, depending on how much recomputation you want to do. The additional recomputation necessary, but it's bounded above by a full additional 4 pass. Total training memory. Therefore, a good heuristic answer for will this model fit for training is the model memory plus the optimizer memory plus the activation memory plus the gradient memory. So you have to train, you have to store the model weights, you have to keep the optimizer memory, you need to then do the activation, so that forward pass, and then gradient memory. Okay, let's see whether they plug in some numbers in there. Distributed training. I'm gonna read this. Where does one keep the optimizer memory in practice? Do you keep it on the CPU? Obviously not, because this is about VRAM, right? So you keep it on the actual GPU, you keep your optimizer memory, your model memory. Why do we have a copy of the, why exactly do we have a copy of the model memory? Gradient memory. Activations. In the case of full recomputation, we need L times H times B times S. Patch size, so the number of tokens, and for all of them we need hidden dimension. Okay. Because this is just a current layer, right? Why do we need L if we're doing full computation? If we're doing full recomputation, it looks like we would need less than that. This might be a bug. Okay, distributed training. Sharded optimizers. The massive memory overheads for optimizers is the primary motivation for sharded optimizers such as 0 and FSDP. Okay, I actually want to read FSDP because Fairsec uses it, so I might take a bit of time to read this on the next stream. Let me put that in here. I'm not that familiar with FSDP, but it's probably similar to what I've done with DeepSpeed and Megatron, etc. Okay. Such sharding strategies reduce the optimizer overhead by a factor of number of GPUs, which is why a given model configuration may fit at large scale, but OOM at small scales. If you are looking to calculate the memory overhead required by training using a sharded optimizer, you will need to include the equations from the figure below. For some simple calculations of sharded optimization, see the following figure from the Zero paper. Note that POS plus G plus P are commonly denoted as 01, 03, 02, 03. So in the first one, we shard only the gradients, parameters, and optimizer state, I guess. 0, 0 is commonly means 0 disabled. Okay, so in the one, we grab optimizer states, which, as we saw before, require a ton of memory, and we shard them across the GPUs. So that means we keep only 1 over n of that optimizer state on a particular GPU. In the 02, we go and take the gradients as well, and then finally we take the parameters as well. So obviously we're trading off compute for memory, because now in order to do a forward pass on this particular GPU, you first have to do the reduce, like some type of distributed communication to gather all of the parameters, and then you can do the forward pass. In the language of this blog post, assuming mixed precision and the atom optimizer, for 01, the total memory is, we need the model memory plus, so this is divided by n, plus activation plus gradient. For 02, we additionally put all of these underneath the same, and then there is a 03 live parameters. Okay, where dp degree is just number of GPUs, unless pipeline and or tensor parallelism are applied. Let's see what's this page they have. I'm not seeing anything. Let's see where it loads. Note that 03 introduces a set of live parameters. This is because 03 introduces a set of config options. Stage 3 max live parameters, stage 3 max reuse distance, prefetch bucket size. They control how many parameters are within GPU memory at a time. Larger values take more memory but require less communication. Such parameters can have a significant effect on total GPU memory. Note that 0 can also partition activations over data parallel ranks via 0R. This would also bring the memory of the activations above the tensor parallelism degree T. For more details, read the associated 0 paper and config options. Yeah, no worries, Sergey. Note in GPT-NeoX, this is the partition activations flag. If you're training a huge model, you would like to trade some memory overhead for additional communication costs. And activations become a bottleneck. And as an example of using 0R along with 01, okay, fair enough. Why is it called 0R? Okay, let's wrap up this blog. Parallelism for LLMs comes in 3 primary forms: data parallelism, pipeline or model, or tensor parallelism. These parallelism schemes split the parameters of model across GPUs. Such schemes require significant communication overhead, but their memory reduction is approximately, for the parallelism, model memory divided by this. Okay, and then for gradients, those are only divided by pipe barrel size. Okay, so this is yeah, thanks Sergey, no worries. I'm happy you found it useful. Okay, note that this equation is approximate due to the fact that 1, pipeline parallelism doesn't reduce the memory footprint of activations, and 2, pipeline parallelism requires that all GPUs store the activations for all micro batches in flight, which becomes significant for large models. And 3, GPUs need to temporarily store the additional communication buffers required by parallelism schemes. So yeah, the computation becomes a bit more difficult and cumbersome. Okay. So with this number, I'm just like super confused. Why do we need so much? I literally have 48 gigabytes. It's impossible that we need 48 gigabytes for our 650 million parameter model. Something is off. Something is completely off with FairSec. There is no way that we need 48 bytes per parameter, even more. In that case, for a billion parameter model, we need 48 gigabytes. That's like just, there is no way. When 0 is combined with tensor and or pipeline, the resulting parallelism strategy forms a mesh like the following. Okay, we already know this. Okay. The 0-2 is forbidden with pipeline parallelism. Is this still the case? Assert that this is smaller than incompatible. Okay, this is still the case. Gathers the full layer parameters from other ranks, processes a full input on the now local full layers, then frees the memory that was allocated to hold the remote ranks parameters. Tensor parallelism gathers the remote activations for the local input from other ranks, processes a partition of the input using the local layer partition, then sends the next layer's activation to remote ranks. For the majority of Eleuther's work, we train with pipeline and tensor parallelism along with 0-1. This is because we find 0-3 to be too communication heavy for our hardware at large scales, and instead use pipeline parallelism across nodes along with tensor parallelism within nodes. Putting together everything for a typical 3D parallel 0-1 run with activation partitioning, we get this. Okay. So there is the model memory. To optimize your memory because of 0-1 activation and gradient memory. Nice. Very insightful, Black. Kind of combining ideas from various papers I've read before into putting them into like simple formulas. Okay. Let's just think for a second. Optimizer state. Let me see whether optimizer states. Okay, they do include the copy. So just for the optimizer, we need 12 bytes. For gradients, we need worst case. So worst case, 12 bytes plus 4 bytes, that's like 16 bytes. And then for activation, and then for model, so again, total memory is this. So 4 bytes, let's say, plus 12, that's 16, plus for gradient, let's say 4, that's 20, for activation. So like worst case, we're looking at like 24 bytes per parameter. Like that's like unimaginably bad implementation. And in that case, let's see, calculator, 24 bytes per, and then we have 615 million. So that's like what, 14 gigabytes. Memory required. So then why do we need so much then? I'm literally using over 40 gigabytes to run the 650 million parameter model. Something is completely off. Plus we are using the memory efficient atom. Okay, optimizer memory, activation memory, gradient memory. This makes sense. This makes sense. I'm not sure why is activation memory only across. Let me see what I said about that. Activation. When sharding the activation, 0 can also partition activations over data parallel ranks. Tensor parallelism gathers the remote activations for the local input from other ranks. Processes a partition of the input using the local layer partition, then sends the next layer's activation to. Okay. Why are we using so much memory? It's completely not clear. Okay, super useful blog. I'm gonna share this one with people here. beyond me. Why am I using almost 48 gigabytes of VRAM for a 650 million model in per sec? I'd expect something even in worst case. Assuming 4 bytes for frames, threads, activations, 12 bytes for Atom. With 650 million, that's like what? 17 gigabytes? Or what we calculated some number before. Let's just see. Calculator again, assuming 24, 615 times 24, like 15 gigabytes. Okay, guys, I am wrapping up the stream, and let's continue in a bit less than 2 hours. We're going to read the FSTP paper from FAIR, and also continue pushing through the work here. Let's see with Stopes. I think we're done. Okay, filtering is actually done, so we have everything we need. The data is filtered out. Filter out new. So here's our data, and then I can now run maybe the data preparation stage in the background, and then get back to you guys in like roughly 2 hours. Catch you soon. Hopefully you found this stream useful, and see you later, guys. Bye bye.